Hello everyone, it's an honor to present our paper Uncertainty-Aware Label Distribution Learning for Facial Expression Recognition. Label ambiguity is a key challenge in facial expression recognition, or FER for short. Images in existing FER datasets are labeled with only one emotion category. However, in real-world scenarios, facial expressions of people can be complex and they tend to express multiple emotions simultaneously. This can lead to noisy and inconsistent annotation since different people might perceive and labels facial expressions differently. To solve these problems, we propose to construct emotion distributions for training images from the provided single label and use them to optimize the model. Inspired by the smoothness assumption, we assumed that neighbors near each other in the valence arousal space are likely to share labels. The valence arousal is a continuous emotional model closely related to the discrete emotions. We first used the k-nearest neighbor algorithm to identify neighbors for each main instance. We also utilized the valence arousal value to calculate a local similarity score between each neighbor and the main instance, where higher similarity score indicates that the emotions of these two are more similar. However, since we use an existing method to generate pseudo-valence arousal, these values can be inaccurate and may lead to noisy similarity calculation. To handle this, we leverage the extracted CNN features to calculate a calibration score for each pair of neighbor and the main instance using a multi-layer perceptron with the sigmoid activation. We call this adaptive similarity, where the local similarity is multiplied with the calibration score to adaptively adjust their similarity, and we obtain the contribution degree, or the weight, for each neighbor. To predict the emotion distribution for the images, we use a classifier stacked on top of the CNN features via a softmax activation. We aggregate the neighbors as the linear combination of their distributions weighted by their corresponding contribution degree. We finally generate the target label distribution for the main instance from the provided one-hot label vector and the aggregated neighbor distribution. These two distributions are balanced by a learnable value called the uncertainty factor. This value indicates whether the model is more confident about the provided single label or it should be in more agreement with the neighbor information. To train our model, we used the standard cross-entropy loss between the constructed target label distribution and the predicted distribution of the network. To further enhance the discrimination of the model and thus mitigate the ambiguity, we also incorporate an extra discriminative loss. We evaluate our method on three popular datasets for in the wild facial expression recognition. Following previous works, we use accuracy as the evaluation metric. For noisy label setting, as we can see, our method helps improve the performance of the baseline significantly and also outperform recent work by a large margin. For cross-dataset evaluation, our model achieves the best performance on all three datasets and surpasses the current state-of-the-art methods. On the original clean datasets, our model also achieves state-of-the-art performance and better than previous approaches as well. We show some emotion distributions recovered by our method on mislabeled images on the top left. At the top right, we visualize the estimated uncertainty values of some training images. At the bottom, we compare our model with the user study where we asked participants to choose the expressions on random test images. We can see that our method can give consistent results and closely agree with human perception. To summarize, we proposed a new method to handle the ambiguity problem in FER by constructing the target emotion distributions for training images instead of the provided single label. The experimental results verify the effectiveness of our approach over current state-of-the-arts. Thank you for listening.